This is the podcast for the journal Neuropsychopharmacology. I'm Cynthia Graber. There's a hormone called Ghrelin that's secreted in the stomach, and when someone is hungry, it contributes to that feeling of hunger and the need to search for food. But neurological studies have suggested that Ghrelin might also play a role in compulsivity and impulsivity, and it might be related to substance use disorders.
There are some studies that suggest that, if you give, for example, mice or rats, give them Ghrelin, that they will show more compulsive behavior in order to receive a certain substance. Like they might increase their lever pressing in order to receive a certain substance that they have been addicted to before, like alcohol, for example, or cocaine. And there are actually even studies that show something similar in humans. So there are also studies that suggest that if you, for example, give humans who are already heavy drinkers, who might already have an alcohol addiction, that if you give them Ghrelin, that it will also increase their craving and their alcohol-seeking behavior.
Rebecca Boeme is an assistant professor at Linkoping University in Sweden. She and her colleagues decided to use human subjects to investigate how Ghrelin affects reinforcement learning, basically how Ghrelin influences decision-making when subjects receive positive and negative feedback, and also how it might actually be affecting the brain. To do so, they had healthy volunteers come to the lab twice. Once was for a placebo version of the tests, and one was under the influence of an increased level of Ghrelin. During this time, the participants did a number of tasks, including a reversal learning task. They'd see two different symbols on a screen and had to choose one. They'd learn to associate one symbol with a higher probability of receiving money, and the other was associated with losing money.
But then after a while, there will be a reversal. So it's a switch of the probabilities. All of a sudden, the other symbol becomes the one that wins more often. And so you should adjust your behavior. You should then start to just choose this behavior, choose that symbol that is now the good one. And then it goes back and forth. So when people learn this, at some point they reach a certain criterion. So we see that they start to choose one of these symbols way more often, and then we switch the symbol that is the good one. And so people have to just adjust, and they have to learn, like, okay, after a while there will be a switch, and then I have to adjust my behavior. But it's important to know that you don't always win with one of these symbols. So what happens is that it's an 80% chance of winning, but there's a 20% risk of losing also. So not every time you choose like what is currently the good symbol might be the one situation where you win something. Sometimes you will lose, but you have to actually stick still to the good symbol. So that's a way how we can basically evoke prediction errors in our participants. So they will learn the symbol is a good symbol, but then after a while, there might be one time where they lose, even they're choosing the good symbol. And then they will have a prediction error. So they will think like, I should be winning, I'm losing, this is not what I predicted. And then after you switch, of course, you get a lot of prediction errors because at this point, you will lose a lot, even though you're predicting to win. And so we can evoke a lot of prediction errors in our participants. And that's actually the goal of the whole study. We want to evoke prediction errors, and we want to see how well can they adjust their behavior and how do they react to these win feedbacks and loss feedbacks.
And then the researchers can model that prediction error to figure out, for instance, who's sensitive to punishment, and so they'll change more if they're being punished. The model comes up with calculations for what's called punishment sensitivity and reward sensitivity to describe the individual's behavior. What they found is that during the Ghrelin session, people were less sensitive to punishment than during the placebo session, but there was no difference for reward sensitivity. Dr. Boeme, did that surprise you?
This was actually what we expected. So we did expect that punishment sensitivity specifically would be altered. So I'm very happy about that we found that. Maybe a bit more surprising were the findings on the brain level, because here we didn't have a completely clear hypothesis. We thought, okay, it might be something in the basal ganglia and the striatum, because we know that the striatum is very important for processing prediction errors. Specifically, the ventral striatum is known to process prediction errors, and then dorsal striatum is known to play a role in kind of like how you use these prediction errors in kind of the action aspect of learning from an unexpected outcome. And we thought like one of these areas might probably show an effect, but we didn't really know where. And so we had three different regions of interest, the caudate, the ventral striatum, and the putamen. And the caudate is considered kind of the dorsal part of the striatum, while the ventral striatum is considered a region that's important for prediction error processing. And this dorsal part is considered to be important for how we implement these prediction errors, what kind of action we choose based on them. And what we find now in our study is that we see that there's more activity in this dorsal part of the striatum, in the caudate, in the Ghrelin session. So when people experience a prediction error during Ghrelin, they will have more activation of the caudate compared to the placebo session.
And what does this tell you?
We don't know exactly what it means. It might mean that people show more effort basically in implementing these prediction errors. Maybe it's a stronger reaction basically to experiencing something unexpected, and then they put more effort into responding to it. They might be showing more of a flexible response. And I think that is something that could make sense if we think about it from kind of more of a evolutionary perspective, because if we think Ghrelin has to do with foraging and trying to find food in a situation where you're starving, then you have to avoid being afraid of risks, avoid, not taking maybe a kind of a risky behavior. If there's punishment, like maybe in that nature, that would be kind of like you get hurt, you have to keep running even though you're already exhausted, something like that. So you have to be less reactive to the punishment, basically.
So are there any particular weaknesses in the study?
One thing we have to consider is that we gave them an infusion of Ghrelin. So, this is not a natural state. We don't have people who are actually fasted and are hungry, but we gave them a lot of Ghrelin. So it's a high amount of Ghrelin, and maybe this is something that wouldn't typically happen like this in our daily lives, at least not in our daily lives, where we are usually fed, right? In our, at least the Western societies, we tend to not be hungry. So this is a state that we don't typically experience. So if we want to relate this to, substance disorder, for example, this might not specifically represent what happens in the brain of somebody who eats at a normal rate and then, shows more compulsivity or impulsivity in response to substance use. So that's something that needs to be considered. But I think it's still nice to kind of use this model to first understand the very basic mechanisms, what's going on, how does Ghrelin affect reinforcement learning? And then I think it would be a next step to kind of go more into, like, first of all, an area of more like an ecological level of Ghrelin, and then also at the same time look more at actual substance use disorder conditions.
That's actually what I was going to ask next. This is certainly early research, but are there potential implications in the future for clinical care?
I think it would be interesting to look at if there's changes in Ghrelin levels in people who have substance use disorder, for example. That could be a first step to see, does this actually have an effect? Is this maybe altered? Could the Ghrelin system be a system that is altered in people who have developed a substance use disorder? So that would be one way to look at it. The other one would be, it could be very interesting to look at, just these early stages also of the development of substance use disorder. So phases where people are just kind of getting started with using substances. If, adjustments of Ghrelin levels here could have an effect on if they will then express compulsive drug use or not.
And so what types of research do you think still need to be done?
I think there's still a lot that we need to understand actually about the basic function of Ghrelin. So we still need a lot of more basic research on this. This study is just, kind of like a small piece to the puzzle. We still don't know all the functions that Ghrelin has in the body and all the consequences it has based on relation to brain activity, in relation to behavior that people show. But then also more clinical studies where we actually look at Ghrelin in clinical populations. And substance use disorder specifically, but also different psychiatric conditions could be interesting. There are some studies that look at Ghrelin also in anorexia. So there are different conditions where this could be of interest. And I think, that it's still a kind of a young field. So I think there can be still a lot that can be done.
This is the podcast for the journal Neuropsychopharmacology. To read the article discussed in the podcast, go to www.nature.com/NPP. I'm Cynthia Graber.